Okay everybody, this is Dr. Pennington again. I have a very quick video here on things called frost circles. We're not going to focus too much on these in terms of the grand scheme of things for the aromaticity chapter, but I thought it would be useful for you guys to see them. If you've looked through any of the material about aromaticity and what makes something aromatic, you'll have seen that there are several criteria. I'm not going to go through all of those because that's for my determining aromaticity video, which is also up there. But one of the things it talks about is a number of pi electrons within the system you're talking about. And typically, for something to be aromatic, you want what's called 4n plus 2 pi electrons for something to be aromatic and stable. And conversely, something that has 4n pi electrons is known as anti-aromatic, which is unstable. The only real issue is, yeah, it's useful to know these formulas, but knowing those formulas doesn't really tell you why something that looks like it could be aromatic is actually really unstable because it's anti-aromatic. And these frost circles will help a little bit with that. So I have a couple of examples that we're going to go through to hopefully make it clear. But again, it is not going to be a huge focus. I just wanted to let you guys see how these frost circles work. So I have four compounds here. You can see they're all conjugated, they're all cyclic. For all intents and purposes, they're all flat, sort of. We're going to go through some justification for exactly why some are aromatic and some are not. Now, based on what you guys have seen before, when you look at this, you can see this is Cyclo Butadiene. The number of pi electrons that it has is 4, which fits this 4n formula where n is equal to 1, which makes this anti-aromatic. Now what that means is that it's not stable at all for some reason, which conversely, compared to benzene, which we know to be aromatic and very stable, there must be a reason why, and it's really to do with the electrons involved in the pi system. And so I'm going to show about these frost circles. What I've drawn is, for each compound, I've drawn a circle and then taken the structure of that shape of the ring and put it so each vertice hits the inside of the circle, where the point arranged on the bottom, and that's particularly important. Oh, bollocks, man. Assholes. All right, okay, forget that screen that just came up. At least it wasn't anything suspect. Anyway, where were we? We are here, okay. And what I've got here is each of these black lines here represents one of the sets of molecular orbitals that come from the pi system here. I don't want us to worry too much about what those mean, but that's what each one of these black lines represent. And you'll notice there's one arranged at each place there's a vertice of the shape. And then there is a dotted line here. So we have molecular orbitals that are stable, lower in energy, and then molecular orbitals called antibonding orbitals that are higher in energy further up. The dotted line here represents the middle point. The idea is, for a frost circle, you want, for something to be stable, you want all the electrons in the pi system to be paired up and below the midpoint of your frost diagram. If they're not, or if they're unpaired, then that's going to cause some particular problems. So if we start off with benzene, for example, you'll see the midpoint is right here. There's the dotted line right in the middle. I've got 6 pi electrons in benzene. You can see that for the 6 pi bonds, because there's 3 pi bonds, I'm sorry, and 2 pi electrons per bond. If I fill these electrons in, lowest orbital first, hopefully it makes sense that there go 2 electrons. Let's do a different color for the others. There's 4. And then there's 6. Can you see that I've filled in all the bonding molecular orbitals? I haven't gone above here, and they're all paired up. That makes this lovely and stable, and is one of the reasons why benzene is aromatic. But when we come over here, let's choose some green. Let's look at this. How many pi electrons do we have here? Well, we have 4. If we do the same thing, we're going to fill these electrons up first, but then when we get to the next orbitals, can you see these two are degenerate? They have the same energy, therefore I have to fill them half each. And 1 electron in each orbital, this essentially makes for something like a radical, which is not stable at all. These are very reactive, and that's why this is unstable. Anti-aromatic means unstable and reactive, not happy at all. Benzene's very stable, this guy is not. Okay, now let's go over and look at these other two. This is called Cyclo Butadiene. How many pi electrons here? Well, here there are 4, all right, as I'm sure you can see. And the question you're going to ask yourself was, well, is this stable or not? Is it aromatic or anti-aromatic? Well, you already know from this formula it's anti-aromatic. And the reason why is exactly the same reason as for the cyclopentadiene here. You've got unpaired electrons. It doesn't matter where they are on this energy diagram. They are unpaired and therefore not stable. Therefore, that's why this is anti-aromatic. Now, let's look at this guy. This is kind of like cyclopentadiene. This is called the cyclopentadienyl cation. So I've removed a hydrogen here, but I still only have 4 pi electrons. Okay? So can everybody see what we get here essentially is I have 2 electrons here and then I have to fill them in here and here. It doesn't matter that I can move my electrons around the ring via resonance. This is still anti-aromatic according to this formula and according to this Frost diagram. Therefore, that's why this is anti-aromatic and not stable. Hopefully that makes sense. Now let's go to a couple of others. I have some more examples here just of larger rings, and I've drawn them out underneath, so hopefully you can see what's going on. There are 1, 2, 3, 4, 5, 6, 7 carbons here. This is called cycloheptatriene. This is a cycloheptatrienyl cation. There's 6 pi electrons because there's 3 pi bonds. And if we fill the electrons in, can you guys see what we do is we do this, and then we fill them in. We fill in all 6 pi electrons. So that makes this aromatic and therefore stable. I can move the plus charge all the way around the ring through resonance. Okay. When we look at this guy, this is called Cyclo Octa tetraene. Because there's 4 double bonds. Now, how many pi electrons here? Well, the fact is there are 8. All right. So if we just fill them in, 2, 3, 4, 5, 6. Now we're going to come across a problem here similar to what we came across with these guys. I only have 2 electrons left, so I have to place them here and here. All right. Technically, that would make this anti-aromatic and therefore very unstable. This ring is big enough that it allows itself to be flexible, so it can actually pucker up a little bit and make itself into kind of the shape of a boat, sort of, which makes it not aromatic at all. This is actually called non-aromatic for something that's not planar. But hopefully you can see why there's no way this guy can be aromatic according to its Frost diagram, and it's not. Now the last 2 that I want to show here are very close to each other. They're both based on cyclopentadiene. One's the cyclopentadiene cation, the other is the cyclopentadiene anion. And you'll notice they are different in terms of the number of electrons. When we look at this guy, we actually did this one back here. And it's still the same as it was before. There's 4 pi electrons. I have to fill them up like so, so therefore this is anti-aromatic and not stable, just as you would have seen from the 4N formula anyway. This guy, on the other hand, it turns out this guy is aromatic and much more stable. And that is simply because if I ask you to draw resonance structures for this, you could draw out a whole bunch of resonance structures where the negative charge moves around the ring, which means that these electrons must be in a p orbital in the pi system if you can resonate them around. Therefore, we include those in the total number of pi electrons in the system, which ends up being 2, 4, and 6. And because we've got 6 pi electrons, I'm hoping you can see we end up with no electrons that are unpaired, making that much more stable and aromatic. And so that's how Frost circles work. Hopefully that makes things a little bit easier to understand why some compounds are aromatic versus anti-aromatic. All right, thank you.